look at some actual code. Okay, so the other thing is, especially when we get to GPU level stuff, if you click on this, it will bring up, it goes to GitHub, pulls it into Google's Colab, and then you can actually run it here. And I think I've got it set so that it even pulls in the data, so it'll just run. So if you need a GPU, you don't for these initial ones. And in fact, the CPU on Colab is going to be slower than your laptop. But anyway, know that you can just click on this little doohickey and it should bring it up. Okay, so I've got a whole bunch of visualization stuff here. You can just ignore it. What you care about is we're going to be using Pytorch to do a bunch of stuff, but you're familiar with Numpy. So first thing I'm going to do is I'm going to show you how to solve some model training problems using Numpy with some manually computed symbolic derivatives, slopes. And then I'm going to show you how to convert everything to Pytorch. And then show you how it actually will do the computations for you to figure out where you are on the lost surface. Okay, let's see. And I think I'm using the scikit-learn regression models just to check my work and to draw some lines. Okay, so this is all just my supporting code for graphics and so on. Okay, so this data set for cars, you'll use this in the machine learning course, but or actually I stuck it in here as well. You can see I'm just writing it into a subdirectory called data and the cars. And so you can see that I've got cylinders, engines, and weight, and miles per gallon is what I'm going to use as my target most of the time. Okay, so let's say that we want to do, what I want to do is draw a nice line. I want to come up with the coordinates, the model parameters. This is the beta 1, beta 0, or weight and bias. If you want to think in neural net terms, I want to figure out what the slope and y-intercept of this line is, okay? So I could try randomly trying combinations of these and compute the mean squared error and see which one's lower. And the way we do that, I think I may have stuck this in the wrong spot here. But anyway, this is what the lost surface looks like. So what I could do is try different combinations along this surface. It's a matter of randomly picking points and then going upwards and seeing what the loss function is. If you want to look at it from above, this is what you'd see. And so we can just try searching this slope intercept space. And literally, I've just got nested loops here that do that. I'm saying try slope in between this value and this value. Now, because I didn't want to wait 3 lifetimes for this to terminate, I deliberately chose values where I knew that somewhere in between this range was the actual slope I needed. And the same is true of this. Otherwise, it would go forever. Here's my model. Got a slope times the weight vector, the weight of the car. Just happens to be a vector, right? It's this thing. And so here's my linear model. This is my prediction. This is my known correct answer. These are my residuals. This is my mean squared error. Okay, so that's my loss function. So I have a model and I've run my entire X vector through it for some value of M and B, which I'm iterating through all possible combinations of. So I'm going to try to get a Y for every possible combination of M and B. I compute a loss function, and then I'm just saying, well, figure out which the best one is. If my loss is better than the last time, then keep track of the loss and the slope and the y-intercept, and then just print those out. And you can see that I eventually get to the point where I've discovered that the lowest loss is somewhere in here. And then I go, oh, okay, well, I know what the coordinates are then, and that's what that is. And those are exactly what we see here, are these things. So this is.
You seem to be cheating a little bit, Terence, because you already know where those things are, so you are using all of this.
Yeah. If I didn't know this, this would still be running from 3 months ago when I tried writing this thing. Right? If you increase this at all, you will spend forever. So this is brute force, and I'm simply saying that when we're training, we're going through a search space, basically, trying to find the best parameters to give us the lowest loss. Okay, so that's obviously not how we do it. So what we do instead is we use an indication of where we are on the surface of the loss function to tell us which way to move our parameters. The direction to go is in the negative of the derivative, which is the slope, so the negative of the slope. Our loss function is the error, the residuals, squared. And I don't put the 1 over n on there because it's a constant. But so that's our loss function. And so a little bit of calculus later, and I compute the derivative in each direction. And so I get this residual times x, or the residual. And that is what you're going to see in here. So this is nothing more than telling me which direction the slope is. So this I happen to know because I happen to know a little bit of calculus. We're never going to have to do this manually, but I'm taking you using Numpy, and I'm going to move you into Pytorch, and then I'm going to show you how to do the automatic gradient computation in Pytorch automatically. Okay, so I'm starting you from scratch in Numpy. We don't know anything about Pytorch yet. Look at my learning rate, super slow, and there's a reason for that. Anyway, so I'm starting my slope at a random location, and normally I would start this at a random location too. But it turns out that I haven't whitened my data at all. I haven't normalized my data, and so this would take a billion years to train if I don't get it close to that. So once again, I'm going to cheat. So remember the code. I'm going to do it a bunch of times until I get bored. I'm going to get bored in 100 complete iterations. My prediction is the slope, whatever that is, randomly assigned, times all of my training x, which is just the weight of the cars, and then add some bias. And I can even get away without that if I want. What is my residual? What is my loss? It's the square of that average. And then I'm saying, all right, if this is the loss, in this case, I don't actually need the loss except for printing it out because I've manually computed the symbolic derivative. But this gradient, this derivative, tells me the direction to go. I'm going to go the negative of that, and I'm going to scale it by some learning rate. The problem I have is that the learning rate for this direction has to be really big, so I make progress. But if I make it too big, it'll bounce across in this direction. And that's why you see this note here. It's almost too fast for the slope, but I need to crank it up as much as I could, but it's still going to be super slow for B, so I had to get it fairly close. So when I run this thing, question?
Yeah, can you have, like, this might be a dumb question, but can you have two learning rates, like one for B and one for M?
Oh, yes, you can. And that is exactly the direction we're going to go. That's definitely something that will dramatically improve the convergence rate on this. And it will happen sort of automatically. We'll still talk about a single learning rate as a general step, but we're going to use something called Atom, or we can use RMS prop. There's a number of things we can use that will have a different learning rate. Oop, I'm going to get my chat going here. Sorry, I missed somebody. Oh yeah, thanks, Yannet. You got to install Pytorch. Yeah, you definitely want to have multiple steps per dimension. So, but in this particular case, we don't. We're just using a single learning rate, and we're multiplying it by the slope in that direction, but in the opposite direction. So you can see we're tweaking M and B. We start them out randomly. I'm cheating here slightly, but we move them. We keep tweaking them down towards lower and lower loss. And then when we get bored, after 100 epochs, we stop and print it out. Notice I didn't get the best line here. Okay, so if you guys have downloaded that, you don't need Pytorch yet, try to play around with this. Change that starting y-intercept to be 5 and see what happens.
A quick question about these values of M and B. So is there some standard rule how you pick this? Like you said, if you took some other value, it's going to take forever to find the correct value.
This is, I'm trying to introduce the minimum bit of technology and library functions possible. But it means that I'm using an incredibly naive approach that is not practical, even in this simple case. And so I had to cheat, otherwise this thing is not going to work. And so so the exercise is, what happens if I make this 5? Okay, so I rerun it. Look at my line, it's worse, right? Because it didn't get this anywhere. That's because look at my learning rate. So it works fine. You can see the loss function dropping dramatically at first, but it doesn't get any better because this learning rate is way too slow to get 5 up to 45. So if I get it closer, it's just not showing. It's because look at this learning rate. It's showing out. It's moving, but very slowly out in like 4 or 5 more digits. So this is the minimal example I could get you that only did some vector stuff, but it's not the greatest. So you want to try this and just see that it's really terrible. Okay, so we can fix that trivially by doing what I suggested earlier, and we don't want a loss function like this. Now we can make it work with a more sophisticated thing. As Nicola was saying, we can use different learning rates per dimension. But it's easier if we simply normalize the data and make the loss function look like this. And then a single learning rate does a great job. And so now I'm going to do the exact same thing, except I'm going to normalize my data first. So once again, I'm taking my values. Oh, and I'm just converting that to Numpy. But I'm mean shifting it and then dividing by the standard deviation. So now X is normalized. And then I'm leaving Y alone, but I got to get it in the right vector shape. Okay, so I have the exact same code that I did before, except now both of the parameters of my model are trained starting from random positions. Notice my learning rate is much higher, and notice the number of epochs is 1/10 as big. And everything is exactly the same. This is the exact same loop, except for this part. It's the exact same loop. And now when I run it, look at this, I nail it. Now, of course, the y-intercept is different. And that is because, of course, that I've normalized this X. Instead of being, 2,000 and 5,000, it's -1 to, So check it out. All I did was normalize my data, and all of a sudden, this trivial little loop here trains my network. Now, of course, you guys are probably thinking in the back of your head, yes, but we did this in linear regression with just a little bit of math mumbo jumbo, right? And we got an exact solution, none of this iterative crap. And that's absolutely true. However, when you go beyond simple linear regression, in fact, you go to logistic regression, or you add some regularization, you most likely will have to do some iterative solution like this, okay? All right. So now let me move you from Numpy to Pytorch. So all I'm going to do instead of mp.array is I'm going to say torch.tensor. Tensor is just n-dimensional array. I believe a mathematician would tell you it has something to do with the rank as well, but I don't know anything about that crap. So I'm just doing torch.tensor instead of np.array.
Why are you reshaping, Terence?
Because it made my vector multiplication work better or something like that. But basically, it's really just they're just vectors, but I wanted it to be a column vector, I think. Yeah. There was some reason
the linear layer wants a two-dimensional tensor because it's expecting in general more than one variable.
Yeah, I'm not using the Pytorch standard model, so yeah, I'm getting there. So all I'm doing now, so I showed you how to do NumPy to solve the problem. Now let's do the exact same thing except use Pytorch. And again, we're doing all of our own stuff. The only difference is that I'm using Pytorch tensors. So instead of np.std and np.mean, I'm doing torch. So I've normalized my vectors. And if you look at this loop here, instead of initializing with this random thing, I do this random junk. And oh, I am doing the auto grad here. So instead of having to manually compute my own derivatives, I'm using some magic within Pytorch to actually compute these for me. When I call loss.backwards, so in both cases, I'm computing the loss. The only difference is here, when I call loss.backward, what it does is set this field called grad in M and B. Okay, so instead of m underscore grad and using it multiplied times that, I'm multiplying m dot grad. So this sets a hidden field in M called dot grad and B dot grad, okay? Why? Because this loss function is a function of M and B. Now, how do I know that it tracks those and not like X and some other stuff? It's because I used this requires grad equals true. And if you look up here, there's some English blah blah that will explain this in more detail for you. The key is I no longer have to know any calculus because it's not really relevant to the situation here. I just need it to be able to make this thing work. And then I would have preferred this was above this, but it can't because this value doesn't exist yet until I actually do this loss backward once, but then I would have wiped it out. Anyway, trust me, these need to be in this position. So after I've used the values, I need to zero it because I'm going to come back around and do it again. Okay, so when I update my learning rate, and this Torch no grad, that just says, don't keep track of my gradients. It's doing automatic gradient computation using something that I think we went over briefly in class called operator overloading. It's constructing an expression tree in memory to keep track of all expressions that are a function of variables that have this requires grad thing true. Anyway, so we don't want to monkey with this. And so I say, look, just anything inside this block, don't do this torch stuff. And anyway, you'll get used to that. The loop is almost identical. We just don't have to manually compute our symbolic derivatives. So I run this thing, assuming I guess I have to start from the top here and run all the way through. Let's see if we can do that here. There we go. Okay. So once again, I get a decent solution through here. And we're at 648. Okay, so I've got some exercises for you here. So what you should do, and I've got the full solution if you want to just dig through here, but you're basically going to solve the same problem, except for instead of weight to MPG, you're going to use the engine size and horsepower to MPG. It's super easy, but it'll get you used to doing this thing. Quick question for you. Why, you'll see that it's true for this one as well. Why do both of these models have the same 23.44 as the y-intercept after we've normalized? Anybody remember that from linear regression? I don't know if you went over that. It's basically because once you've normalized your data, beta 0 is y bar. It's the average of y. So 23.44 is basically this little thingy in here. So if you normalize, that's an easy way to get beta 0. Okay, so that's the first notebook, and you're just going to have to, dig through this. It's easy to run. It should just run for you. You can go through, and there's plenty of blah blah on there. So again, the idea is you start with Numpy, but you've got to compute your own derivatives. So let's flip to Pytorch and let it compute the derivatives for us. And it's really just another numeric library, except it also knows how to run all this stuff on the GPU in parallel. So, and there are, tens of thousands of processors on a GPU, as opposed to the 8 or whatever you have on your laptop.